So my plan was to give a little bit of recap,
Mhm.
conclude, and then we can do questions. Is that okay?
That's very okay.
Okay, great. Um, so yeah, just to recap and sorry, in the last part I really rushed, but what I'll try to do, I'll just try to give a big picture overview and talk a little bit about open challenges and where I think we should be putting some efforts, some of my ideas on that topic. Okay, so I started the tutorial by talking about how learning of living beings is amazing, and it's very very different from how we have algorithms in deep learning and machine learning. And then I try to contrast Bayesian learning, which is more like human learning, with deep learning, and uh, present to you how they are, different, and what are their pros and cons. And then my goal was to put these two fields together to bring them closer. And for that, I started by writing Bayesian principles in the form of an optimization problem over probability distribution. And these distributions, these approximations, are trying to approximate the posterior distribution, which comes from the Bayesian principle. So what I showed to you is that if you take a particular type of gradient algorithm, when you apply it to find the posterior approximation, and by changing the form of the approximation, you can derive many different types of learning algorithms. So we went into deep learning algorithms like gradient descent, Newton's method, and then variance adaptive learning rate algorithms like RMS-prop and ADAM. Um, and then we also talked about how this all relates to classical, textbook examples that you read in on Bayesian inference. So like least squares and Kalman filter, HMM, they all have, some property where it can be written as a special case of the same principle that explains some of the deep learning algorithms. And then very quickly we went into how then we can use this idea of putting two different fields together using some principles. Well, once you put them together, then you can borrow strength from each other to improve one another. And what I showed you is how you can take the deep learning algorithms and you can put certain Bayesian principles in there, and they essentially come out to pulling the expectation out of the gradient. So just sampling models instead of just having one model. And that simple change helps you to improve things. And then in the last part, very quickly, I try to contrast, the simple solutions that we have with the very difficult problem that we have in hand, with some warning of how difficult it is to compute uncertainty. Um, and if we could compute uncertainty, then the problem of lifelong learning would be solved to some extent, to a large extent, I believe. But then that's the problem, and then I try to give you an alternative um, way to compute posterior distributions in neural network, which is like working in the function space. So we didn't really get into that much yesterday, but maybe today we can talk a little bit more about this. So I just wanted to give you a bit more insight into this open challenge. So the bigger question that I started with was how do we achieve lifelong continual type of deep learning which mimics the behavior of the learning process of living beings. And the bottom line that comes down to is that, well, you want to compute some kind of uncertainty. You want to know how much you don't know, so away from the data. Then that's a very difficult question because that boils down to computing the exact posterior distribution. or maybe better flexible posterior approximation to it. But as you can see, and we very quickly looked into this from going from gradient descent to Newton method, you go from a Gaussian with only mean to Gaussian with mean and covariance. If you want to compute higher order information of your landscape, higher order statistics of your posterior approximation, they're related to higher order gradients of your landscape. So essentially, the problem of knowing how much you do not know comes down to really studying the higher order uh, properties of the optimization, the loss landscape. And that's very, very hard because that's going to be very complicated because all we can do scalably right now is to compute gradients and some part of Hessian, and we can't go beyond that. So what I've been actually thinking about is that if you directly try to solve the problem in the simplest and straightforward manner, it's going to be very, very hard. So you have to be a little bit more clever and think outside the box. And so I try to remove all these jargons and try to bring it to simple, although more philosophical and vague question. But then let's try to bring that down to the math that we know. So the first question is what do we know, right? And this question is what we are actually doing in deep learning right now, meaning that if I give you a bunch of data, you can fit it very well. You can figure out what the data is telling you mostly. So like some common patterns that are supported by a majority of data points that you can pick up by fitting a loss using a very flexible model like neural network. So it seems like that we are very good in answering that first question. What do we know? If you give me a lot of data, I'll figure that out. But the second question is the complementary question of it. Well, I know this much given this data, but then what do I not know? What have I not seen and I might see in the future? Or the other things that are not present in my data set. And this question is essentially related to uncertainty. Right? So uncertainty can be of many types. It could be uncertainty in your current model. It could be uncertainty due to a wrong model that you have chosen. So there could be other explanation of the data set, right? It could be uncertainty due to the noise in the data. And there are many, many types of things that you cannot actually imagine right now. So that's a difficult question. But actually, if you realize this, how we learn, we don't really pay attention to what I do not know. We don't really think about everything that I do not know. So if I want to learn about something, then I look into what I know and then I try to use it to learn a little bit more. And the things that I need to learn a little bit more, these are actually related to the third question here. So what do we need to know? And that's an essential question. So if we can figure out, knowing what we know and what we don't know, what do we need to know? Then it's sort of exploration at the edge of your knowledge. It's the thing that you should know in the near future. And this is related to exploration, action and exploration, to take action, to collect data, to improve your knowledge from what you have right now, your current state of knowledge, and you want to expand it. And I think this is how you're going to think about it. You want to think about uncertainty. You don't want to think about everything that you do not know, but only the things that you need to know right now. And so there's this question about what is relevant and what is not relevant. And this is the thing that I kind of showed you some pretty pictures from this MNIST digits of, you can figure this out of what is relevant and what is not relevant and what you should be learning about. So there's some hope. And the way that I think about this, and there's a very beautiful paper by Carl Fristrin And these thoughts I have been kind of thinking on my own, and then I read this paper last year, and I was very intrigued that he has written many things that I was thinking about. Um, and essentially, you can think of models as, so you have world is very big, and your model is fit on some data examples, and it's a window to the part of the world of what you've seen now. And approximations are actually even kind of telling you which part of the model is important. So it gives you some tractable, so you have very complicated neural network, but then the posterior approximation is telling you just look into the first and the second order information of that model. And what you want, actually, you want to take some actions so that you can improve your approximation right now. So you want to sort of fill in the data space, thinking about what is relevant and what is not. I'm not sure how much of my own thought I'm able to give it to you, but I'm happy to discuss more about this in the questions session. Okay, so I'll stop this philosophical discourse at this point and just conclude. So this all these things that I'm telling you in the first part, at least, will be out in this. It's work in progress. It's kind of becoming better every day. So hopefully, in 1 or 2 months, we will have the first version complete. And thanks to my co-author Howard Rue, who has been helping me in writing this paper. Many other people, this is like from 2016, 17, 18. Many of these people, actually, my collaborators who helped me to take the first few steps of what I have presented to you today. And recently, these set of people have actually worked with me in 2019 and this year. Uh, all of this practical deep learning stuff on large scale was done with these people. Continual learning was done with some of them. Then the function space stuff that I didn't talk about much, but was done with these 3 students. And Pierre Elkir is a colleague of mine who has been helping me understand this sequential learning problem. And Pingbo was also an intern here. He's also he also contributed to the continual learning problem. So with that, I will conclude the presentation and we can go into the question.
Perfect. Thanks. So we have now collected some questions from the audience, and there is this question that says, since Friston's work was mentioned, I wonder, what do you think about Dasgupta et al., a theory of learning to infer from the Tenenbaum-Gershman labs? If you have heard of it, if you're familiar with it.
Sorry, what is it? Theory of?
So it's the theory of learning to infer. The author is Dasgupta et al., and it is from the Tenenbaum-Gershman labs.
Ah, okay, yeah. So I don't remember if I've seen that exact paper, but I have followed, Josh Tenenbaum's work and colleagues. So from what I understand, they're actually going towards this kind of thing, like learning to learn and uncertainty and all this stuff. So yeah, I don't know that exact work, but it's very related.
And well, a bit connected to this is, which ideas in machine learning do you find underrated?
Underrated?
Yes.
Oh wow, that's yeah. I mean, I think that somehow. So we are doing deep learning right now. I mean, this is again an opinion, but this is an exciting question. It helps me think. So we are doing deep learning right now, right? So we are all like really into give me data, I'll fit it. Give me data, I'll fit it. So we are like really greedy. And then there's this other thing about like taking action and go out there and do exploration and try to learn and collect data. But then most of the effort is in reinforcement learning, right? And I think there's a huge gap between the two. So this whole idea of taking action to collect knowledge, to improve your knowledge, I think this is not really mainstream. So, self-supervised learning is somehow being put in that way of like I want to reduce my dependence on the labels. So I want to go out there and then try to formulate the problem such that I can use my current data to to figure out what's important, and that I think is good. But active learning is something that is very, very underrated. And when people learn, they always kind of go out there and think about like, what do I know, and what do I want to know, and then based on that, I kind of pick some things out. So I do this exploration at the edge of the knowledge, and I think there isn't much work as far as I know. It does go, exploration in RL is a big thing right now, but then it's really, really extreme. Like people are not trying to think about picking examples to make better data sets, or or instead of doing gradient descent, stochastic gradient descent with random mini batches, try to select those mini batches more carefully. Um, and I think this is a central thing that's missing. It kind of comes in different fields under disguise, but I think that should be the main thing of like active exploration.
And if we are staying within the realm of Bayesian machine learning, Bayesian deep learning, and you were advising someone who is starting their career in research, in which direction you will point this person? Which are the topics that you consider these are so future interesting areas in Bayesian machine learning, Bayesian deep learning?
So is the question in terms of like open problems to work on, or is it about like beginners to learn about the area?
Yes, open problems that can be exciting to develop research around in Bayesian methods.
Yeah. I mean, I actually think, and this is again my opinion, that, you know, this is a new time that the Bayesian inference that we knew, I mean, that I knew that I was working on, in the last decade, uh, that all of those ideas, they're very useful. And at the principle level, they make complete sense. So this idea of uncertainty of what you do not know, and let that guide your learning of, what to know. But right now, with deep learning coming in, these are very different kind of models. So I think the theory that is being developed for this kind of probabilistic graphical models, where you have these directed graphs, and the knowledge is being put in place by a designer. So these are not black box models. Uh, the theory of Bayesian inference actually breaks down, or requires modification, requires kind of fitting to the new modern things that are going on. So to state in a simple word what I'm trying to say, how do you take these classical ideas that exist in Bayesian statistics, and then try to use them in deep learning, in this modern concept, is really not uh, explored properly. So we have methods like MC dropout, which kind of empowers people, and people think that, wow, I can now be Bayesian, I can run this MC dropout, but it's really just scratching the surface, because if you go anywhere a little bit farther from these kind of simple methods, then your computation becomes very, very difficult. So there is need of like innovative ideas on how to take those existing ideas of posterior averaging, or marginalization, or model selection, and then try to use those ideas in an innovative way in deep learning. This is not trivial at all. So like active learning is also experiment design. It's called Bayesian experiment design. Is a very, very old field, maybe like 70, 80 years old. And there's lots of ideas there that have not at all used. And if you actually ask people who have been in the field for a long time, they would say Bayesian principles are the way to think about the problem of all these sequential problems. But we don't do any of that right now. So I think that there's a lot that can be done in theory, in practice. And I could talk about this whole day because this is what I do. So I'll stop here.
And also related to this, well, about 10 years ago, the field of Bayesian nonparametrics, it was very popular. There was a lot of work done on Indian buffet and so on. And now it has a little bit disappeared from the map. It's less known. Do you see it making a comeback, especially with new ideas that
Yeah.
you're doing research and so on?
Yeah, that's a really great question, right? So these methods were like more classical Bayesian inference, right? They were designed with this idea that you have structure in your model that somehow keeps the statistics that we were using useful for the new thing. So now that you're stacking layers on top of each other and just putting loss functions and adding them together, designing architectures, uh, it's very hard to put those old ideas in this new framework. And I think, in a way, this is my personal biased opinion that some of those old ideas are probably not useful. Like the idea of you know choosing number of clusters, for example. I mean, there's a full chapter in Bishop's book about this, where variational Bayes is useful for doing Gaussian mixture model. But it becomes a textbook example, unfortunately, right now. And I don't know how this will be useful in the near future, at least. The non-parametric methods, of course, we're seeing that Gaussian process is making a comeback, and there is a direct relationship between neural network and Gaussian process. So that helps a lot. But then other types of non-parametrics, uh, you're not sure if to write some theory it has been useful, but I'm not sure how that fits in. So we need to reinvent ourselves if we are really thinking about deep learning and we want to do these kind of things around it. Although those ideas are useful for many other things other than deep learning. So I'm not sure if those will be making a comeback in like next 5 years at least. But again, there are principles, right? There are some ideas there why we were actually thinking about these non-parametric methods, and those ideas at the core could be useful, even if the methods are not useful. So that's my take on that.
And well, in recent years, the field of interpretability has gotten a lot of attention. It has become very relevant, both from a theoretical standpoint as well as in applications. And do you see Bayesian methods contributing, and where do you see the contributions?
Yes, yes, definitely. So I think this idea of I mean, it's not really interpretation, but regularizing the problem. This is a very central kind of, I mean, it's a machine learning concept, it's a statistical concept. And in Bayesian inference, by putting structure in your prior, in your model, you can actually force the model to restrict the model to stay within, a limit. So in the new way, what you could see is that you could put structure in your posterior approximation, and that should also help you to distill knowledge from the from the network. So, for example, if you do a Gaussian approximation with a certain structure, so you say this layer is going to be dependent only on the next layer, but no other layer, then that sort of helps you to distill certain types of knowledge, right? And I'm I really believe that this is a very powerful mechanism. It's actually is related to doing this type of intervention that you could choose an approximation and you could say, let's see what result do I get, and then based on that you can change your approximation to something else. And these ideas have not been really exploited that much in the community. So I really believe that there's something in this, and that we're actually working on some of these things. So hopefully in a few months you will see some of this stuff. So I'm very hopeful. I think this should be an exciting area.
And so we were discussing yesterday and a bit today the topic of lifelong learning, and there is also another name that maybe is connected or maybe not, called never-ending learning. Is this the same thing? Are there different fields? Are there differences?
Yeah, I think it was from what I know. I think in natural language processing, some people did the never-ending learning, which I mean, I think the goal is the same. The way these things have been implemented are probably different, but it doesn't really matter, right? These are just jargons, like just different words put to. So I would say they're same. I've kind of read some papers on this. That's my understanding. I might be wrong.
And well, we started the session with an example, so from your daughter playing guitar. And the question is, what are your sources of inspiration? Is it, for example, what you see in real life with your children, or where do you get inspiration for your ideas?
Yeah, I mean, this is so. I mean, for me, when I was a PhD student, I wasn't really paying attention at this, and I was actually going to Toronto sometimes, and I was talking with some deep learning people, and they were working on AI at that time. Um, and it took me, some amount to have this maturity in me to be able to kind of zoom out and look at the big picture. And I really started thinking about this after my PhD. And then I started teaching, and I had, my daughter was born at the same time. So all of these things sort of come together when I was reading a lot of text, for fundamentals of machine learning, fundamentals of learning, like behavioral uh, psychology, and some of this work, like the book by Daniel Kahneman and other popular science books that people have written. It actually comes really together that there is the way that people behave, the way that living organisms behave. We I mean, of course, we want to exploit that behavior because that's the only optimal thing in front of us that we know right now. We don't have that many gold standard to look after. So I actually read a lot outside these technical topics and to get inspiration on these things. So I read a lot of like neuroscience, popular science books, and some on economics and some on psychology. And sometimes I also attend workshops and talk to people. So definitely, I have been inspired by science in general, social science also, to kind of come up with this big picture problem that is quite broad and appeals to many people. And I think this is a good idea to do.
And so there is a question on base with approximate posterior. Is it possible to find a family of distributions P with specific properties which are closer to other in Q?
You'll have to repeat the question and be a little bit slower, so I'm having
Yeah,
difficulty.
no problem. So on base with approximate posterior, if it is possible to find a family of distributions P with specific properties which are closer to another one in Q.
So a distribution in the space of all distribution, which is closer to the approximate distribution, the set of approximate distribution. Is that what the question is?
Yes.
I mean, this is so I am not able to understand the question because uh, maybe I'll just say what we're doing in approximate Bayesian inference is exactly this, right? So we have a distribution, posterior distribution, in which is one point in the space of all distribution, and then we restrict this the space of distribution like Q. So that's the approximation, and we try to then find a member that's closest to the truth. So that's exactly what we're doing. So this problem of the objective function that was written as expectation of the loss minus entropy, that's actually equal to the KL divergence between these two, a Q distribution in the space of big Q, for trying to find that best approximation in the KL divergence sense. So that's exactly what we do. So I hope that makes it clear. If I don't know if I answered the question.
And well, now the field of machine learning is very competitive, and also I am sure that you have a lot of candidates whenever you're looking for collaborators and students. So whenever you are deciding whom to take, what do you pay attention to? Which are the areas in their CV, their profile, the research that catch your attention?
Yeah. So I really say it very strongly. Like I try not to look at the name of the school, and I have to really kind of like suppress all my biases to not look at the age of the person or like not look at the gender of the person. It's hard, but what I actively look for is is a sense of like is the person promising candidate in terms of what projects I'm thinking about right now. So do they have the kind of skills that can be useful for things that we're trying to do in the next 2 years, for example? And so that's the like technical match. And usually it's not like you need to have a NeurIPS paper or ICML paper. I really don't look like many of my members had like actually no prior experiences in machine learning, so I don't look for that. But I really would. I try to think about like if people would join the team, what would happen on day-to-day basis? Like how hard would they find when I say, oh, the eigenvector of this matrix is is this matrix is positive definite, or and then person has to kind of be at the same page as me. So I try to think about like this level of technical expertise, and if it's sufficient for them to take on these challenging projects, because some things that we're doing are very difficult to do. Then the other things that I think about is creativity. So if person has wider interest, and if they are somebody who will be good to work with the team. So like have to be a team member, need to be creative, think outside the box, and not just have like the usual CV. And then have the minimum kind of technical excellence that will help them do their day-to-day things. Those are the three things that I'll say.
Great, great. And if you go back to Bayesian questions, is can we recover all optimization algorithms using Bayesian principles?
No, probably not. Um, I mean, the there's lots of like, for example, constrained optimization algorithms. This is one place where um, the principle that I wrote actually will not work, um, because it just kind of doesn't handle, right. So the distributions are usually they have like this kind of support, and the support is infinite most of the time. You could go to truncated distributions and work with them, but then still expectations are some kind of like smoothing over things. So in optimization, you have these hard constraints. Some of them are harder to capture through distributions because they're like inequality constraints. So those are a little bit difficult. One thing that we've been working on is showing that duality in optimization can be derived from Bayesian principles, and that actually works. And you will see some of these results in next month, few months, year. So there is lots of like overlap between the fields, but not all of optimization is a subset of the Bayesian principle. So that's my answer.
And the intersection of Bayesian deep learning and non-convex optimization. Can you say there is some words about what having achievements? Where do you see areas of research or problems?
Yeah, so this great question. Actually, this has not been explored that much, and I don't think people write it in this way because so think of like deep learning, then non-convex optimization, and Bayesian methods. These are three things. And usually, when you think about Bayesian, you don't think about optimization. So, what I presented here is sort of trying to bring these fields together. So, because deep learning is related to optimization, lots of tricks are borrowed from there. If you write Bayes as optimization, then you can kind of put everything together. Um, One thing that is very underappreciated is this view of when you take neural network and you take their width and you put it to infinite, it becomes a Gaussian process. Okay, so essentially what this actually says is that if you go to infinite with problems, then your local minima are kind of like disappearing. They're all becoming global minima because Gaussian process is a unimodal posterior. It just has, it depends on the likelihood, but likelihoods are like usually this kind of classification, Bernoulli or multinomial likelihoods for classification, or regression is just Gaussian. Then in those cases, the distribution is unimodal. And this kind of connects to this result in kernel methods that, in function space, you can write problems as convex problems. So most of the solutions in like kernel methods, they resort to this convexity in RKHS, and the GP result is also related to that. So GP is also based on kernels, and unimodal posterior means you have a unique global minimum. Sorry, not unique, but you have a global minimum, and not have any local minimum. And this kind of connection is not really utilized. And this is actually the reason why when you do sequential learning in the Bayesian way, you always kind of get one answer. So you don't forget because there's only one posterior distribution. So actually the optimization problem is convex, strongly convex in the space of distribution. So there are all these properties that's actually not utilized or not even in theory literature. So I think there's a lot to do here. I don't know if that made sense. Sorry, this is like some of it is like very technical, and I've been thinking about it alone for a while, so may not make sense. But if you want to know more about this, maybe get in touch with me through email. That'll be nice.
So how can someone approach you for research opportunities?
How to approach who?
If someone is interested in working with you as an intern, a postdoc, or related, what is the best way to reach you?
Yeah, so I mean, we get a lot of emails, of course, but emails are the best way. And we have actually, like for me, I don't know if the question is just for my group or in general, but for okay. So for my group, we have an email list for these job applications. So you could send an email to that Google group, and somebody will look at it at some point and respond to you. And I also put it on my webpage if we have open positions. We will probably have one open position coming up, but every year they should come out maybe like end of the year for the next year, because April is the start of financial year in Japan.
And one last question is, how did you get started in machine learning?
I
Yes, you.
You okay? So I this is very very yeah. So I was master student. I got lucky to I got admission in some very good institute in India. It's very very hard for people have there's lots of exams and it's very difficult. So I got into this research program, and then I was a little bit late to join because I had my exam going on. So I joined a little bit late, and all the professors were gone. So I was given an option to do this and do a project in signal processing, and I started working on some like brain signal processing, brain computer interface. It used to be called in 2002, and then I got some data, and then I was trying to do some data analysis, and I learned about signal processing methods like Kalman filters and HMM. And then I started, like, when I do Google papers on this, I started finding all these papers by Zubin Garamani and Sam Royce, who wrote a lot of these things, and you may not know now because he passed away a few years ago. And Kevin Murphy, who was my PhD supervisor, and I read their papers. Tom Minka, lots of these people at that time wrote wonderful papers on Kalman filtering, EM algorithms, Gaussian, linear Gaussian models, and that kind of formed the basis for my own and what I use every day right now. So I was very excited to see that machine learning people really are not scared of doing everything. Like, they take this math from stats, and then they write MATLAB code, and then MATLAB used to be the standard at that time, and they would put it online. And I sent an email to Zubin Garamani, and I said, I need your code, and he replied to me, at that time, and I used his code, and I wrote my thesis with that, and this was very exciting that I could, apply math on a real problem, and I wrote an IEEE paper on this all by myself without, like, very little supervision because there was no machine learning at that time. So I think machine learning, that strength still remains to the day, that we have lots of code available, we are very applied, but we are also kind of strongly rooted in theory. And that was my beginning. So I worked on statistical signal processing. I use EM algorithm. Then I worked on control application for 2 years in a company, but my heart really wanted to go in machine learning. So, like 2007, I started a PhD in machine learning with Kevin Murphy, and that was my beginning. But yeah, it was a fun little thing that happened to me.
Oh, well, that's a very interesting story. And with this, we can basically finish our session. It was really great, interesting days. We covered a lot of ground, and I'm sure that all the audience was very excited to listen to you, not only here in Zoom, but also on our live broadcast on YouTube. And well, as you mentioned, if anyone has questions or would be interested in collaborating, they should reach out via email. Otherwise,
Yes.
well, we're finishing nicely on time. And thank you very much for this today's MT. And well, I will wish you a nice day. And tomorrow we will have Pierre, so someone from your group. So we're also very excited to have him on. Um,
Great. Yeah. So yeah, if any of you have more questions and just want to talk, feel free to send me emails. I sometimes am slow, but I definitely respond. Even if I respond maybe like 3 months after, I do respond to people mostly at least one time. So yeah, please send me an email, and I'm happy to discuss and help you in any way in your career if you need me. Thank you, and thanks for organizing and giving me this opportunity.
it was a great session. Well, then have a nice day.